Hello everybody. Welcome to video lecture on Introduction Post's Correspondence Problem, Rice Theorem in Turing Machine. The agenda for today topic is Post Correspondence Problem, PCP. Definition of PCP. Modified PCP. Reducing MPCP to PCP. Rice Theorem.
Here we are going to first define post correspondence problem, which is also called as PCP, and then with the help of an example demonstrate PCP. PCP is a simple problem of undecidability. To understand undecidability, let us look at the type of problems given to our computer systems. Every problem given to the computer systems are divided into two kinds, those that are solvable and those that are not solvable. Solvable problems are those when given to the Turing machines, that is our computer systems, Turing machine halts. Solvable problems are further classified into decidable and undecidable problems. Decidable problems are those for which the Turing machine halts when the answer is yes and also halts when the answer is no. For example, when you want to determine whether input number is a prime number or not, then let us consider the number 3 as input. For this, the Turing machine halts as 3 is a prime number, and when given a non-prime number, say 10, the Turing machine says not a prime number and halts. In both the cases, the Turing machine is halting. The other kind of solvable problems are undecidable problems, for which the Turing machine will halt if the answer is yes, but when the answer is no, the Turing machine may or may not halt. PCP is an example of undecidable problem. Let us consider the 4 tiles as shown. These tiles are called as a collection of dominoes. Each tile consists of a top and a bottom. For example, tile 1 has B on top and CA at the bottom. We need to find a sequence formed by elements on the top similar to the sequence formed by elements present at the bottom of the tile. Say for example, we formed a sequence by tiles placed in the order of 4, 3, 2, 1. This is shown here. Then the sequence formed by the elements on the top are A, B, C, A, B. And the sequence formed by elements at the bottom of each tile is C, A, B, and CA. We note that the top sequence and the bottom sequence do not match. For PCP, we need to find a finite sequence arrangement of tiles such that the sequence formed by the elements on the top must be same as the sequence formed by elements at the bottom. To find this sequence, the tile may be used as many times as we want and may be placed in any order. That is to say that the tiles can be repeated and arrangement can be in any order. Say now if we arrange the tiles 1, 2, 3, 4 but in the order of tile 2 first, followed by 1, followed by 3, followed by 2 and followed by 4. Then the sequence formed from the top elements is A, B, C, A, B, C. And the sequence formed by the elements at the bottom of each tile are A, B, C, A, B and C. This is a sequence where the sequence on top and the sequence of bottom is a match. Hence, we say that a solution is found. PCP is simply a problem to determine whether a collection of dominoes has a match or not. The match should be a finite sequence, and sometimes if we often find an infinite sequence, which leads us to the conclusion that the problem is not solvable or unsolvable. Let us now consider another example. There are 3 tiles or dominoes. Tile 1 has 1 0 on top and 1 0 1 at the bottom. Tile 2 has 0 1 1 on the top and 1 1 at the bottom. Tile 3 has 1 0 1 on top and 0 1 1 at the bottom. Now we need to find a matching sequence. We cannot begin with tile 2 because the first elements on the top and the bottom do not match. Similarly, we cannot start with tile 3 because the first element of the top of the tile is 1 and the first element at the bottom of the tile is 0. So there is no match. So we cannot begin with tile 3. So the only obvious choice is to begin with tile 1. Now, when we place tile 1, then we get the sequence 1 0 on top and a sequence 1 0 1 at the bottom. Now we find that 1 at the bottom has no match. Therefore, we need to consider another tile. Let's say that we go for tile 1 again. In this case, the top sequence becomes 1 0 1 0 and the bottom sequence becomes 1 0 1 1 0 1. Now this has led to a sequence where 2 elements at the bottom of the sequence are not having a match. Therefore, considering tile 2 at position 2 is not good. We need to find another solution. Let's say that we consider tile 1 at the beginning, and when we consider that we find 1 which is unmatched at the bottom, we consider tile 2 for the second position. In this case, if we look at the third position of the bottom and top sequence, we find that there is a mismatch. The 0 which occurs at the third position on the top does not match with the element 1 which occurs in the bottom sequence. So this also has no match or solution. So our obvious choice would be left. The obvious choice that is left is having this tile, placing tile 3 after tile 1. So when we do that, we get an extra 1 at the bottom sequence. To match that, we can consider once again tile 3 again. When we do that, we get another 1 which is extra at the bottom. This clearly shows that there is no match or solution for this problem. And therefore, we can conclude that this problem will always have an unmatched item and we will get an infinite sequence. Therefore, we can conclude that this problem has no solution.
Rice's theorem. So just we are having a brief discussion about the examples and what we have to prove with Rice's theorem. Now coming to the definition, any non-trivial property about the language recognized by a Turing machine is undecidable. So this we have to prove that for a Turing machine, we cannot say that the non-trivial property will be possessed or not. So this problem is undecidable. Okay, and this theorem is named after the Henry Gordon Rice, who proved this theorem in his doctoral dissertation of 1951, right? So the problem is named by this Henry Gordon Rice. Okay, so here we cannot say that, like halting problem, like PCP problem, we cannot say that there exists or there may exist an algorithm or a machine that can predict whether the Turing machine will hold this non-trivial property or not. Okay, so such type of machine, like for halting problem, we were assuming that a machine exists that can predict whether the machine will halt for a particular input or not, and for PCP problem we were predicting the machine that can give the output as the PCP is solvable or not. So for this Rice's theorem, we cannot have such machine that can take the description of a machine and the non-trivial property as input. So this P is representing the non-trivial property, and such machine, we are assuming that such machine should predict whether this property is possessed by this Turing machine or not. But in practice, there is no machine that can always decide whether the language of a given Turing machine holds a particular non-trivial property or not. So we cannot have any such machine that can predict whether this non-trivial property P will be held by this particular Turing machine or not. We cannot practically have any such machine. So we have to prove this with these steps. As this we have already discussed. Rice's theorem states a non-trivial property, and by property we mean that we mean that the language of all Turing machine that satisfy that property. So language of all the Turing machine that satisfy the particular property P, right? So here, if P is a non-trivial property, for proof we are taking P as one of the non-trivial property that we are taking as example, and we will be proving that this property is non-trivial, right? So here we are taking P as non-trivial property and the language holding the property. So P is a property that is non-trivial. So P is a non-trivial property, and the language that holds the property is, we are calling it L of P. So the language of machines that hold, or all the machines holding the property P is identified by L of P. So the language is L of P. Now we also have some Turing machine M that recognizes this property. Now we have to prove that for this language of this non-trivial property, every machine M, for this particular language, every machine M must possess this property. And this language, if we have any such language that says that this property is possessed by all the machines M, all Turing machine M, is undecidable. So we have to prove that this statement, this language is undecidable. We cannot write such language, means we cannot be sure of all the machines. Suppose this property is possessed by M1 and also by M3, but not by M2. So if we have any such machine that doesn't possess this particular property, so the property is not trivial, the property is undecidable and non-trivial, because all the machines are not possessing this property.
In this class we discussed about post correspondence problem, PCP, definition of PCP, modified PCP, reducing MPCP to PCP, Rice theorem. Thank you.